Hello and welcome back to Unit 9 on impulse and momentum. In this part, we are going to focus on inelastic collisions and explosions, which is really just an inelastic collision backwards. So as a reminder, two types of collisions. Elastic collisions conserve both energy and momentum, whereas inelastic collisions conserve only momentum. Inelastic collisions can conserve energy, or maybe not conserve is the bad word there, but some do better at keeping the energy than others. So we're going to begin by looking at a simulation. If you click on this link, it takes you to this website, and we're going to go into Explore One Dimensions. In One Dimension, I want to look at the momentum, also look at the energy, and you can see the more data boxes checked so that we can determine the total momentum of our system. So right now, ball 1 has a momentum of 0.5 kilogram meters per second. Ball 2 has a negative 0.75 kilogram meter per second momentum, giving us a total momentum of negative 0.25. If I now tell this to go and look afterwards, we can see the kinetic energy, which I forgot to point out before, is constant. If I again add my momentums together, 0.63 negative plus 0.38 will be negative 0.25, so that is constant. And the reason for that is right now my collision is completely inelastic. Let's see what happens if we change the elastic to, say, 75%. Reset the collision. That should have reset it. Did it reset it? Oh, this is weird. Okay, back to where we started. Look at momentum, look at energy, show more data. And again, we're at 75%. So now we see we no longer have the same amount of energy. Our total momentum still adds up to negative 0.25. And the behavior of the two balls in this case is very different than what we had before. If I again decrease the elasticity, though I am sure I'm going to have to reset this whole thing again, rather annoyingly actually. And so again, a different behavior. We still have a change in our total momentum of negative 0.25. Our energy has dropped by quite a bit at this point. Bringing the elasticity down again to 25%. We now only have 0.04 joules of energy left from our initial of 0.44, but our total momentum is still negative 0.25. And notice at this point that the two balls after the collision are both moving in the same direction, although one of them is moving very slowly. Okay, one last time. We will again do everything, bring the elasticity down to 0, and tell it to go. Our kinetic energy is 0.02 joules, which is the smallest value we've seen for after the collision. Our total momentum still adds up to negative 0.25. And notice here that the two balls are moving off together with the same velocity. It's like they've stuck together with Velcro. That behavior where they stick together is a hallmark for a perfectly inelastic collision. Let's return to the PowerPoint file and do an example. Here we have a railroad car traveling along a frictionless track. You're told the speed of the railroad car before the load drops into it. And you want to know how fast does it move off? And is energy conserved for this? With these problems, the best thing to do is to draw a set of pictures. What's happening before versus what's happening after. So here I have my railroad car moving at its 18 meters per second. And I don't know what's supporting the load, but something is supporting the load and it is not moving. Afterwards, we have the car with the load sitting on top of it, moving off together with some velocity. And that velocity is part of what we want to find. Because momentum is a vector, you want to define a positive direction, and that positive direction should be used throughout all of your calculations. So you shouldn't change the positive direction moving from before to after. In this case, since everything's moving to the right, I'm going to let my positive direction be to the right. I can now find the initial momentum of my two-piece system, the car and the load. One piece will be the mass of the car multiplied by the initial velocity of the car, which is 18 meters per second. The second piece will be the mass of the load multiplied by the initial velocity of the load. That works out to be 216,000 kilogram meters per second. After the collision, I have the load and the car moving off together, so I can combine their masses. Multiplied by their mutual final velocity, and that works out to be 17,350 kilograms times V final. Momentum for this collision is conserved, so initial momentum has to equal final momentum. Our initial momentum was 216,000 kilogram meters per second. Our final momentum was 17,350 kilograms times the final velocity, which, solving for that velocity, tells that the car with its load moves off at 12.45 meters per second. The second part of this question asks, is energy conserved? Well, we're going into this knowing that it's not, but let's check it. How can we tell if energy is conserved? Well, we can calculate it. So the initial energy will be 1/2 times the mass of the car times the initial velocity of the car squared, plus 1/2 the mass of the load times the initial velocity of the load squared, and that works out to be 1,944,000 joules. The final energy will be 1/2 multiplied by the combined mass, which is 17,350 kilograms, times the final speed there squared, and that works out to be 1,344,553.3 joules. And as we can see, as expected, our initial energy does not equal the final energy. It's not even close. Therefore, energy is not conserved. For our next example, we're going to work with two air hockey pucks colliding. Before the collision, the 0.2 kilogram puck is moving at 1 meter per second to the right, and after, and before the 0.3 kilogram puck is moving at 0.5 meters per second to the left. After the collision, the 0.2 kilogram puck is moving 0.48 meters per second to the left. And we have the same two questions. What is the final velocity of the other object, which I wrote as a 0.1. It should be a 0.3. I just noticed that typo. Kilogram puck. And again, is energy conserved? So as before, begin by drawing a picture. So here I have the 0.2 kilogram puck moving to the right at 1 meter per second, and the 0.3 kilogram puck moving to the left at 0.5 meters per second. Afterwards, I'm told that the 0.2 kilogram puck is moving left at 0.48 meters per second. And I don't know what, I put an arrow there. That defeats the purpose. I don't know what direction the final velocity of my 0.3 kilogram puck is, so I'm just going to leave it as a generic V final. Okay. Because it's momentum and a vector, I have to define a positive direction. I'm again going to let positive be to the right. My initial momentum has two pieces. The momentum of the 0.2 kilogram puck plus the momentum of the 0.3 kilogram puck. Notice that the velocity on that one is negative because it is to the left. This works out to a combined momentum of 0.05 kilogram meters per second. Oops, that's supposed to be a final. Afterwards, again, have two pieces. I have the piece associated with the 0.2 kilogram puck. Notice that its velocity here is negative because it's moving to the left after the collision. And then the momentum of the 0.3 kilogram puck as well. Multiplying the first term together results in negative 0.096 kilogram meters per second plus 0.3 kilograms times V final. I can now say momentum is conserved, so initial momentum equals final momentum. That results in 0.05 kilogram meters per second equaling a negative 0.096 kilogram meters per second plus 0.3 kilograms times the final velocity of that puck. Solving for V final, we find that V final is a positive 0.487 meters per second. So the final velocities are almost equal and opposite in this case. And the next part of the question is energy conserved? So I can look at the initial energy, which has two terms. The initial energy of the 0.2 kilogram puck plus the initial energy of the 0.3 kilogram puck, which works out to be 0.1375 joules. The final energy will be 1/2 times 0.2 kilograms times negative 0.48 meters per second squared. There's a negative sign up here that I didn't write. It squares away, so it doesn't really matter. Doesn't affect the math. And plugging all that in gives a final energy of 0.0586 joules. One last example. This example is a explosion. Okay. So we have a 5-kilogram object traveling through space at 300 meters per second, and it suddenly splits into 2 unequal pieces. After the explosion that split it apart, the 3-kilogram piece is moving 100 meters per second in the opposite direction from what it was initially moving, and we want to find what is the speed of the other part and in what direction. So what is the velocity? So again, drawing a picture. Here's my object. Make a little dotted line to show that it is going to become 2 pieces, moving at 300 meters per second. After, I have the bigger piece moving 100 meters per second opposite to what it was originally moving. And again, I don't know the final speed of my other object, so I'm just going to leave it as a v final. Initial momentum is going to be the 2 objects together, which is 5 kilograms, moving at 300 meters per second. I'm assuming positive is to the right here, which works out to be 1,500 kilogram meters per second. Final momentum is going to be the 3 kilogram moving in a negative 100 meters per second, plus the 2 kilogram with its final velocity. Just combining terms here. I can again say that initial momentum has to equal final momentum. So 1,500 kilogram meters per second has to equal negative 300 kilogram meters per second plus 2 kilograms times v final. Solving for v final, I get that it is now moving at 900 meters per second in the positive direction, or in the direction that the 2 objects were initially moving. In the next part, we're going to look at elastic collisions. For the moment, this concludes this part.